Bem, boa tarde a todos. Meu nome é Ana Paula Magalhães, eu sou assessora de gabinete do pró-reitor de pesquisa, o professor Silvio Canuto. Em nome da pró-reitoria de pesquisa, eu quero dar as boas-vindas à professora conferencista desta tarde. Quero dizer que foi um grande prazer trabalhar para que ela pudesse estar aqui juntamente com a professora Marie, que eu chamo em seguida para fazer a apresentação da professora Nina Fedorov. Muito obrigada e bem-vindos.
Obrigada, Ana Paula. Eu vou continuar em português. Eu acho que é um prazer enorme a gente receber a Nina aqui na Universidade de São Paulo e ter uma oportunidade de uma discussão sobre como alimentar 10 bilhões de pessoas no futuro. E eu acho que ela posiciona bem a dificuldade e os desafios, na verdade, que nós temos pela frente. O que eu gostaria de colocar também é que a gente está na Semana do Alimento. E é por isso que a Nina foi convidada para vir ao Brasil. Ontem ela participou de atividades organizadas pela Scientific American e a Comissão de Informação de Biotecnologia, onde ela participou, fez uma apresentação e participou de um debate, discussão, o dia inteiro ontem. Então, só para não demorar demais, gostaria de colocar alguns pontos em relação à Nina, que eu acho que são importantes. A Nina, ela obteve o PhD dela, o doutorado dela pela Universidade de Rockefeller. Ela foi professora e pesquisadora durante muitos anos do Carnegie Institution for Science. Ela trabalhou também junto ao Johns Hopkins Institute e ela esteve afiliada na Universidade de Kaust, na Arábia Saudita, onde ela permaneceu por 3 anos montando um centro lá. Depois, voltando para os Estados Unidos, ela atuou como Chief of Scientist, junto ao governo do Clinton. E ela é uma pessoa bastante reconhecida mundialmente por suas atividades na área de biologia molecular de plantas, em vários aspectos. E vai ser bastante interessante, então, ouvir a Nina para que ela venha fazer a apresentação dela. Thank you very much for coming, Nina.
Thank you for that lovely introduction, of which I understood a few words. And thank you for coming. So today, we live mostly in cities. We live in a technologically sophisticated, largely urban civilization. Our shops and our supermarkets are bursting with produce. We have an amazing global food system that brings us food from wherever it's produced, all over the earth, to those of us who can afford it. We have little knowledge of what it takes to produce that food, or what it will take to feed a world of 9 billion, which we expect by mid-century, and 10 billion, if we're lucky, by the end of the century. So I'm going to start with a quick dive into the science and technology that made it possible for the human population to grow to our present 7.5 billion. Then I'll talk about what it will take to keep us, to continue to feed us at the level that we've gotten used to, even as the planet warms and the number of us continues to grow. My deepest concern is not that we lack the technology, but that our rather sentimental urban beliefs about food stand in the way of using that technology. But first things first, how did we get to 7? I think that's interference with the second one. How did we get to our present 7 billion people? Well, for most of our evolutionary history, we were hunter-gatherers. We spent our days finding and capturing food. Then about 10 or 20,000 years ago, we began to settle down and shape plants and animals to our own advantage. Cities and civilizations followed. Simply said, human civilization arose because we figured out how to produce more food than we consume. Now, for millennia, civilization rose and fell, generally lasting as long as the land wore out, or until the neighbors invaded, having worn out their own land. Plants, of course, extract nutrients from the soil. Crop yields decline, making it harder and harder to produce enough food as the number of people grows. Now, a couple of centuries ago, the English cleric Thomas Malthus thought that we were forever doomed to hunger and strife because our numbers inevitably grew faster than our food supply. Now, the global population was just 1 billion when Malthus penned his gloomy thoughts. So if Malthus thought the game was over when we were 1 billion, how did we get to today's 7.5 billion? Now, curiously, it was just about the time that Malthus was penning his very famous essay that science began to enter agriculture in earnest. Now, over the next 2 centuries, innovations in several key areas, synthetic fertilizers, genetics, and the internal combustion engine, transformed agriculture. Plants, for those of you who are not, few of you who are not plant biologists, are magic. They produce sugar out of water and thin air. Well, the carbon dioxide in the air, to be exact. But they also need nitrogen. And plants can't use the nitrogen that's in the air. Now, manure contains nitrogen in the right chemical forms, and it's been used as fertilizer since prehistoric times. But there's not much nitrogen in manure. Around the turn of the last century, the 20th century, Fritz Haber and Karl Bosch figured out how to convert atmospheric nitrogen to compounds that plants can use. Today, that's done in huge factories around the world. As much as the organic food industry wants us to believe otherwise, we simply couldn't have gotten from 1 to 7.5 billion without synthetic fertilizer. Genetics was critical as well. This is Nobel Prize laureate Norman Borlaug, who's considered the father of the Green Revolution. And it's the Green Revolution that set the famine-plagued Asian countries on the road out of poverty. The Green Revolution was based on mutations that let crops take advantage of fertilizer, doubling and tripling and quadrupling yields. Mutations. Mutations are genetic modifications. I'll get back to genetics and mutations in a bit. But there's another major factor that Malthus couldn't have foreseen. And that is mechanization. Agriculture was hard, physical work for most people for most of human history. The populace was largely agrarian, even in most advanced countries, well into the 20th century. As machines gradually took over the work, fewer and fewer people could produce more and more food. People moved to cities, and they continue to move to cities. And the cities became hotbeds of invention and collaboration. Technology-based wealth generation accelerated, giving us all the machines, gadgets, and comforts of modern life. In sum, our modern, largely urban existence came about because we got better and better at growing food efficiently by using science, chemistry, engineering, and biology. The bottom line is that life got better as agriculture got more productive. Most of the world no longer experiences wrong button, the kinds of famines, this is death from famine, that plagued human civilizations from the beginnings of agriculture. Worldwide, the fraction of the populace experiencing chronic hunger has declined. Indeed, it declined from about half of the human population. Everybody was poor a couple of centuries ago, except for the tiny fraction of very rich people. But even as the population doubled from 3 to 6 billion, the fraction of the population that experienced chronic hunger declined from a half to about a sixth, and it's gone down more ever since and continues to go down, except unfortunately for the last couple of years when it's begun to tick up. Now, population growth is slowing, but it's not likely to stop short of 10 billion. We don't know exactly where it will stop. It depends on a lot of things. But the point is that the most optimistic estimates tell us that we have to face the fact that the population will increase by somewhere between 2.5 billion people. But there's another factor, and that is technology is powering the emergence of country after country out of poverty. As people get richer, they want to add more meat to their diet. Transitioning from a grain-based diet to a meat-based diet increases the demand for grain, which in turn increases the demand for land, and of course water. But there isn't any more. In fact, we're losing it to urbanization, desertification, and salinization faster than we're adding it. If we don't change what we're doing, we'll be back to Malthus's predictions within our lifetime. And there's water, of course. Most productive agriculture is irrigated, and the most reliable water comes from deep underground, from fossil aquifers. I worked for several years in Saudi Arabia. Saudi Arabia has no renewable aquifers, and it's used up essentially 90% of its groundwater. What they're pumping up now, and sometimes using for agriculture, is saline water. So they're using energy to desalinate it and then water their crops. So all these indicators suggest that we're reaching the limit of the planet's land and water resources. Yet the population, remember, is still growing. But there's another factor. We're increasingly becoming aware that we must produce food more sustainably than we've ever done so before if we're to leave the land in reasonable conditions for the next generation. What all of this means is that globally we must produce 1.5 to twice as much food each year than we do today. And we have to produce it more sustainably. We have to use less water, less land, water, energy, and less chemicals. Now that might strike you as an overwhelming challenge, but let's put it in perspective. Agriculture kept ahead of a 7-fold expansion in the human population. And all we need is one more doubling of the food supply. How? Just as it was for agriculture, the kinds of advances I've shown you, it's a combination of biology and technology that allow us to both waste less and produce more. All of those, it's not a simple solution. There's no magic bullet. It's a lot of contributions that increase sustainability, decrease waste, and increase productivity. Well, let me give you a little bit, just a little tiny glimpse of the technology that's coming. Today, most of the large tractors on farms are GPS guided. Tomorrow, they'll be driverless. This is what's coming up the pike. So much of this technology is already in use or in the pipeline. Although there are also people on the face of the earth who are farming with hand tools, just as they did hundreds of years ago. So there's a lot of modernization of agriculture that needs to happen. Data on crop physiology are increasingly collected using drones, planes, and satellites, and then fed back to the tractors. The data are used to optimize everything from planting, watering, fertilizing, to pest control and harvesting. Tomorrow, robots and drones will likely do much of the work, from beginning to end. So the large-scale farm of the future might be almost completely remotely controlled by machines. This is all possible, but high-tech farming faces both economic and social barriers. It's expensive. So it only makes sense if it's done on a very large scale. And large-scale farming, often referred to as factory farming, is viewed as socially unacceptable because it inevitably displaces smallholder farmers. Then there's the warming climate. The IPCC's, the International Commission's, new report is out a couple of weeks ago and tells us that we have about a decade left to reorganize our energy economy globally if we're to avoid even more severe disruptions to our lives and our food supply than we've already experienced. But even if we succeed in that undertaking, improbable as it is, we're facing continuing agricultural disruptions from the warming that's already built in to the system. The kind of optimization technology that I've described is important, but it can only get us so far in a shifting climate. The rest has to come from biology, and specifically from genetics. Genes, of course, are what makes us what we are. It's true for plants and animals and microorganisms, all living creatures. And we've been modifying the genes of wild plants and animals for millennia in order to make them better foods, better pets, better agricultural workers. We call this domestication. But it's gene modification. And more recently, we've professionalized the process, and we call it plant and animal breeding. Let me give you some examples of what we've already done. And I find them, even from my perspective of a modern molecular biologist, quite remarkable. Corn domestication began some 9,000 or 10,000 years ago in Mexico. Corn's immediate wild relative is teosinte. As you can see, it's a simple grass. It makes seeds at the top of the plant, and the seeds are frankly hard as rock. They have silica deposits in the surface. Nobody has even thought it possible that they were used as food. This is our modern corn plant. Now, these plants are so closely related that you can hybridize them, and these are the products of that hybridization, except for this one. This is modern corn, and most of this expansion in the size of that anomalous ear, which is not wild and not natural, this is the product of human intervention. Most of this happened in the 20th century. So the earliest ears that have been recovered from caves, even in southern Southwest United States, already had this transformation from being produced at the top of the plant to being collapsed shoots. And then from there, we go to this huge repository of starch and sugars and proteins. Now here's what plant breeders accomplished just for the US in the 20th century. What's shown here in this line is the area planted in corn. What's shown here is corn yields. So you can see that the number of acres in corn has barely changed, but the yield per acre has increased by more than fourfold. That's modern, non-molecular plant breeding. We've essentially done the same with modern wheat, which was domesticated roughly at the same time, within 1,000 years or so, in the Middle East. But the huge increases in global yield happened in the 20th century through the efforts of agronomists like Norman Borlaug, whose picture I showed you earlier. He developed the modern high-yielding dwarf varieties. I recently had occasion to talk about this. It was based on one mutation that happened in nature, and an extraordinary mutation it is. Wheat has 3 full genomes, and it happens that 2 copies of one gene that inhibits the elongation of just the stalk. It's very easy to make mutations that miniaturize the plant, but they miniaturize the yield. What Borlaug and Swaminathan in India did was they used a mutation that was picked up spontaneously in Japan, a miniature Japanese wheat, and that mutation made the 2 copies of the gene product from that gene, of which there are 3 copies, resistant to breakdown. It has to be that protein that the gene makes has to be broken down in order for the stems to elongate. So what he produced was a plant that was miniature in only the stalk elongation, and it turned out to be, there's a bonus to it. The plant put much more of its photosynthate into the grains so that the yields even increased beyond what he expected. And again, that was essentially, it was Swaminathan that persuaded Indian farmers and Pakistani farmers to adopt it. And again, over a couple of decades of what we call the Green Revolution, they tripled, quadrupled, even increased yield by 5-fold. Now let me show you a couple of examples of things that we think are very natural, like this big tomato. But wild tomatoes are small and can actually be quite toxic. Wild bananas are full of seeds and essentially inedible. This is a modern banana. Same is true for watermelon. So all of these differences between the wild relatives and our modern fruits and vegetables, all are the result of genetic changes, and all of them came about through the efforts of people. And one of the most important tools that plant breeders used during the last century to produce new varieties was bombarding plants, particularly, with chemicals and radiation that caused mutations. And I'm going to tell you about the more modern methods, but let me introduce this to you by telling you that it's a little bit like taking a shotgun to the entire complex of genes that you have, what we call the genome, and then throwing it all out in the field and looking for things that are better. Most mutations make things worse, but every once in a while you get something that's better. Now, mutations, of course, are genetic changes, and these crops are genetically modified. This is true whether the mutation happened without human intervention or was produced using chemicals or radiation mutagenesis. But science moves on, and the second half of the 20th century saw a complete revolution in genetics. Scientists learn what genes are and how to add a well-defined gene or a few genes to a plant or animal. Let me give you some familiar examples. Among the best known are what's called Bt cotton and corn. Here's the genetically, oops, wrong button. Genetically modified version, this is the version that is susceptible to the pest. I'm so sorry. The gene, these are protected from major pests by the addition of a gene from a bacterium called Bacillus thuringiensis. If anyone has a cough drop, please bring it up. The gene codes for a protein that's toxic to insect pests, but completely harmless to people and animals. Now, what's really important to appreciate is that this is a step towards sustainability. Globally, we use about 1 billion pounds of chemical insecticides a year. What? Do you want to turn off the air conditioning? No, it's fine. It's just, it can happen. Once you get into a cycle of coughing, it's very hard to get out of it. So the point I want to leave you with is that we use about 1 billion pounds of chemical insecticides a year. Insecticides kill both beneficial insects and harmful insects. Globally, pesticide used to control these insects have decreased by 88% for corn and 59% for cotton. That's remarkable. Now, since they were introduced in 1998, actually not earlier, 1996, GM crops have been adopted by farmers faster than any in the history of humanity. Here are some factoids for 2017. GM crops have been grown on by roughly 18 million farmers in 26 countries on 470 million acres. More than 90% of the farmers growing them are smallholder, resource-poor farmers. The profits are roughly equally divided between the developed world and the less developed world. Now, the next chart shows a graphic summary of meta-analysis of the economic and environmental impacts of GMO crops from 1996 to about 2014. GM seeds cost more than conventional ones. This added cost is largely offset by savings in labor and chemicals, so production costs actually increased less than 4%. That's the increase in total costs. Yields increased by more than 20%. That's argued about worldwide. These crops were not designed to increase yield directly. The yield increases come from decreasing losses. Now, here's the remarkable figure, is that farmer incomes worldwide increased by almost 70%. Obviously, more prominently in developed countries than in less developed countries. Now, the Hawaiian papaya industry was rapidly being decimated by the papaya ring spot virus. You can see what it does to the fruit, but this is what it does to plants. It came back within a few years of the introduction of the virus-resistant papaya. I'm so sorry about this. It happens. I'm going to keep going. Here are examples of familiar food crops that are just coming on the market. Potatoes and apples that don't grow because a single gene codes for an enzyme called a polyphenol oxidase has been turned off. These are now beginning to be marketed in the US. So these are all examples of organisms that have been modified genetically, just like the earlier ones I showed you. But today, only the ones I just showed you are called genetically modified organisms, or GMOs. This doesn't make sense in terms of the science, but that's what's happening. This diagram illustrates the tools that created the first generation of GMOs, so it's called recombinant DNA technology. Is diagrammed here. Enzymes from bacteria are used to snippets of DNA from different kinds of organisms. This is a bacterial part of the recombinant DNA molecule. This comes from any kind of plant and animal. The two pieces are sealed together and slipped into a bacterium to reproduce in many, many copies. That's what made it possible to understand the genes. In other words, only when you could actually magnify a single gene at a time could you actually develop the technology to sequence all the genes. Today that's done. Today that's so cheap that there are even services, I'm sure they're available here, that will sequence your genome for not an exorbitant cost. Now for plants, there's another piece, because you have to get, if you are modifying a gene and you want to put it back in a plant, you have to figure out how to get there. And if any of you have ever visited Washington in the springtime, you will immediately notice these are very old trees. And they have great tumors. Those tumors are caused by a bacterium called agrobacterium. It's a species of soil bacteria that's developed the trick of transferring its own little piece of DNA into a wounded plant cell and causing them to grow like this and produce food to feed the bacteria. That's diagrammed on the next slide. So they have an extra piece of DNA called a TI plasmid, and that has developed the trick in response to signals issued by the wounded plant cell of transferring a piece of DNA. So people have figured out how to slip a new gene of their choosing onto the tDNA and have the plant integrated into the genome of the plant, creating what's called a transgenic plant. And if it's a crop, it's called a genetically modified crop. Now, the latest refinement in molecular technology is referred to as gene or genome editing. The genetic gadget that has become wildly popular just the last few years is referred to as CRISPR-Cas. Now, what this gadget, if you absolutely have to know what CRISPR stands for, it's down here, and it refers to the way that the system, which is a defense system in a bacterium, was first discovered. What this is now able to do, because people figured out how it works, is it uses an RNA molecule to guide an enzyme that cuts DNA to precisely the gene you want to change or edit, which is why it's called gene editing. Once that gene is cleaved, then repair processes in the organism, very similar in all kinds of organisms, can repair it and change the sequence. Let me give you just one example, which isn't out, but it's just so amusing, I can't help but share it. There are hornless beef cattle, but there are no hornless dairy cattle. Now, having learned what gene was disrupted to make hornless beef cattle, scientists were able to use this little molecular gadget, CRISPR-Cas, to disrupt the same gene in dairy cattle. Now, dairy cattle are dehorned by burning off the little buds in calves. Physical dehorning is painful. Genetic dehorning is painless. It's remarkable. Now, let me repeat that today, rather illogically, the only organisms that are considered GMOs are ones that were modified by adding or editing genes, although different countries are approaching the gene editing differently from a regulatory perspective. The kinds of genetic changes made by earlier techniques, including chemical and radiation mutagenesis, and remind you, I told you that using radiation mutagenesis is like using a shotgun on the genome, whereas now we can go in and change one gene, a gene, we know what it does, exactly the way we want to change it. And yet only plants and animals with an added or edited gene are considered GMOs. And these are subjected to expensive and prolonged regulatory scrutiny. There are countries that forbid it completely, that make it very difficult, and just a few countries, including Brazil, that have gotten to the point where it's part of their agriculture. Now, why is, if it's such a sensible thing to do, why is there such a fuss about it? Well, just Google GMOs, and you'll quickly understand. GMOs have been blamed for everything from farmer suicides in India, tumors in rats, and every manner of human ill, from autism to obesity to infertility and cancer. None of this is true, but the images live on in our electronic world, and fears live on in people's minds. For the most part today, people don't know what GMOs are, but they certainly know they're bad. Whoops. Can we get this guy to go?
Do you try to avoid GMOs in your diet?
I do. Yeah.
Tell me why.
There's just a vibration with GMOs. For me personally, just something that I don't particularly want to put into my body.
What does GMO stand for?
Genetically modified. Genetically modified.
The
The I don't know.
Do you try to avoid GMOs in your diet?
Yeah, absolutely.
Why is that?
Just the effects, I guess, on myself.
What does GMO stand for?
Man, putting me on the under the grill. Let's see. I don't even remember.
Do you try to avoid GMOs in your diet?
Absolutely,
Why?
because they're not good for you.
What is a GMO?
It's genetically I don't know, what is it?
If you are eating whole foods, you want to eat what you're eating. You know what I mean? You want to eat what you see. And so, and you're avoiding processed food, but when the whole food is somehow contaminated, that's kind of making it a moot point.
What does GMO stand for?
Genetically manufactured. Oh.
What is a GMO?
General modified ingredient, right?
What is a GMO?
It's something modified.
Do you try to avoid GMOs?
Sometimes. Not a whole lot, but, I try.
What is a GMO?
I don't know. I don't know. I swear. I was just going along with it. I don't know what GMO is.
What is a GMO?
I don't know. I know it's like some corn bad stuff, right? I know it's bad, but to be completely honest with you, I have no idea.
There you have it. So are they really dangerous? Well, the EU issued a report in 2010 summarizing about a quarter century of biosafety research costing upwards of 300 million euros. Its main conclusion? Crop modification by GM techniques is no more dangerous than crop modification by other methods. every credible scientific body that has looked at the evidence has come to the same conclusion, including the U.S. National Academy of Sciences, which issued yet another report in 2016 after reviewing thousands of feeding studies and other kinds of analytical studies. The conclusion is no credible evidence that today's GM crops are harmful to either humans or animals. And yet GMOs remain controversial almost everywhere. In part, the controversy is driven by both organizations and individuals that create and exploit GMO fears for profit. Greenpeace's anti-GMO campaign is one of its biggest money raisers. Why would they give it up? The organic food industry has conducted a deliberate campaign of vilifying GMOs. They haven't even been secretive about it, with the simple objective of increasing their market share. And then there are individuals like Jeffrey Smith in the US and Vandana Shiva in India who make a living by writing books and giving speeches about the imaginary evils of GMOs. They get paid a whole lot more than I do as I give talks defending them, so you can tell where I've gone wrong. So given all the controversy, do we really need GMOs? And the answer is my view, and it's an unequivocal yes. And here's my argument. As population continues to grow, the amount of water available per person gets smaller and smaller. The same with land. The amount of land available per person continues to decline. We can't simply open land anymore. Higher temperatures mean lower yields. Corn, which is also known as maize, fails at about 35 degrees centigrade. Soybeans fail at closer to 39 degrees. Now, the deepest red, is the number of days predicted, number of area, the amount of area in which temperatures will exceed 35 degrees in the stated time periods. This is revolving from 2020 to 2059. So the point is that the deepest red represents 200 days over 35 degrees. So the amount of area that's going to exceed the limits of our crops, which were, by the way, domesticated in a completely different climate regime, will continue to expand. And climate change is already upon us. This is a storm that just wiped out the part of the Florida Peninsula. Totally unprecedented strength. And as climate change continues to happen, we face more storms, which means more flooding, more drought, and fiercer fires. The U.S. has had more than its fair share of all these tragedies. This is from the California fires, this picture. Now let me show you what happens when the food prices begin to increase. This is an old slide, but I think it illustrates the point. The yellow curve is the FAO Food Price Index, and the flags show countries that experienced food riots. That's the 2008 financial crisis, and then prices came down and went up again. Food riots increase as food prices rise. Obviously, it affects the poorest countries first. The Syrian civil war started with the worst long-term drought, arguably since agricultural civilizations began at the beginning of the Holocene in the Fertile Crescent. Now, people fleeing from the Middle East and Africa to Europe are increasingly fleeing the impact of climate warming on their ability to farm. The bottom line is that as population growth continues to grow and the climate warms, and these two factors are closing in on us. We have to adapt our agriculture, plants, and animals to a warmer climate on a decadal scale, not the centennial and millennial scales it took to get where we are. I hope I've shown you that we have the tools to meet both the population crisis and the population crisis. And yet today, the ability to use science and technology, whether it's high-tech, large-scale farming or biotechnology, is strongly resisted almost everywhere in the world. Changing people's beliefs and attitudes, which ultimately determines what politicians do, is slow and difficult. That said, the good news is that we can do it. That we can sustainably feed a growing population, even in the warming world. We have the tools. Question that I leave you with is, will we be able to change our own belief systems and our politicians' belief systems fast enough? Thank you. The answer to that question is, I don't know. I'm delighted to answer any questions you have. And by definition, there's nothing that I define as a dumb question.
Well, we thank you, Professor, for your conference. And now we can ask some questions.
Yes, and it would be good if there are some mobile microphones. I'll stay here, and people could run around. Go ahead. Ask me whatever you want.
Nina, is labeling of GMO products an issue in the U.S.?
Yes, thank you for asking that question. Yes, it is an issue. Again, it came as a deliberate effort on the part of the organic food industry to force people. I mean, they were very open about it. They said, if we can get them to label it, we can drive them out of the market. So the problem is that the foods that are on the market today that are genetically modified are nutritionally no different. And our FDA policy, the Food and Drug Administration, which determines policy on food labeling, has made it clear that we only label foods that are where there is a health issue or an environmental issue. Now, that said, our legislators, our Congress passed a bill last year saying, but genetically modified foods, you've got to figure out how to label them. And they stipulated that it shouldn't give the impression that there's something wrong with them. But of course, the minute you label, you do that. So the job was given to our U.S. Department of Agriculture. They've been stewing around and figuring out how to do this. They don't want to put labels on they don't want to put a sign on the label that says GMO because, of course, it means already I've got to be afraid of it. But they haven't been able to come up with an alternative. The obvious alternatives are you take your cell phone and you scan a product code and you get the information on the product. But not everybody has cell phones, obviously, although it's hard to find somebody who doesn't anymore. So we'll see what comes out of it. We can hope that it's not a stamp on the label. But unfortunately, the impact of it is already being felt because the food industry is driven by consumer preferences. And if the consumer says, I don't want GMO in it, they're going to take it out. And often what has happened is that the nutritional value decreases because the cost of the non-GMO product increases. Who will know that? Only people that look very close. Next question. Yes?
Nina, thank you for your talk. We are possibly about to make changes or to make re-engineering of plants so that we may have even species that already don't even exist yet in the future. Do you think that this could cause a new revolution in the future? And how...
A new revolution in...
A new green revolution in the future. If we could, for example, increase productivity in ways that we couldn't do yet using classical genetics and the GMOs. And if we do that, how the US sees this ethically and legally? Are you already discussing that?
There's about 4 questions in there. The first
I made my 4.
Yeah, the first point is that at the moment, there is no tool that will make one species into another. Species are human definition of, by and large, a genetic separation sufficient so that there isn't interbreeding. You can name many exceptions to that. So I can't rule out the possibility, but the probability is that what you'll see is people starting with something that's already a very productive plant and making it more drought resistant, more heat resistant, more insect resistant, more pathogen. That's been most of what plant breeding has been about. More yield, more resistance. None of that is different than what we've been doing for the last 10,000 years. I don't think there's going to be a huge revolution because we can do things better, faster. The hope is that we'll be able to maintain the productivity, which is enormous. I mean, doubling a 5-fold increase in yield? I don't think so. We will double yields in places where the yields are well below the yield potential of the plant. So the hope is that because this is so much easier to do, countries in which this has been impossible to do because of the cost will be able to do that. I mean, there are little projects in many, many developing countries. I'm thinking particularly of Africa, that really they desperately need. There's a wilt-resistant banana, for example, that's genetically modified. That kind of thing is what's desperately needed. So you're saving things from destruction, and so yield increases follow. I don't think the ethical questions are largely in human applications. And there, everyone is worrying about, well, is it ethical to cure a genetic disease like a deletion mutation, beta thalassemia? The answer is we'll probably begin to accept that we can do those things. Redesigning the germline or doing prenatal fixing of genetic defects, that's probably coming, but people are hesitating about that. What I'd like to point out to people is that what is considered ethical tends to evolve. When in vitro fertilization became a reality, it was thought completely unethical. Well, we accept it today. So I think one has to think about the ethical dimensions, but one can't freeze. There's nothing magical about an ethical system. It evolves as people's cultures evolve. Yes, there was.
Thank you for your talk. of the about 300,000 species of plants we have only domesticated a few hundred. So do you think it's time to start trying to domesticate other plant species that may be more suitable to dry and warmer climates? Is that happening somewhere? Because I've only seen we're just trying to modify the same plants that are already being cultivated.
I think the answer to your question is yes. I think everybody can hear the question. I'm more concerned about trying to understand it because of the distortion. I think that there are projects, particularly in India, where a lot of different grains are used to increase the productivity. The problem is that these ears are unbelievable. And when you can plant the plants this far apart, the yields per acre of simply usable starch and protein are huge. So the answer is probably yes, but I would guess that what will happen is a little bit of what's happening in potatoes. That is, we've learned enough about the genes that that plants naturally use in the wild to protect themselves from things like Phytophthora. Phytophthora is the awful fungus that caused the Irish potato famine that killed so many, in which so many people died. But today what you can do is go to the wild species, pull out a gene or two or three, and put it into the potatoes that people already eat. So that the gene technology enables you to do things you couldn't do before through genetics. So, for example, the diverse races of corn that are grown from Mexico down to, I'm sure there are some here, the land races. The problem with those land races is the yields. They're very poor. Now, it's much resistant, but adding an insect resistance gene to one of those doesn't transform it into a different species. It simply takes what you have and makes it resistant. But if there are traits that turn out to be very important for growing the corn in different climate regimes, people will go after those. As they understand them, they can transfer them to varieties that have already been bred to be extremely productive. That's an incredible progress that's already made that, in a sense, you have to throw away to start again with a wild species. I think it's not by accident that there are so few domesticated species that provide the majority of our calories, and those of animals, because half of the grain grown is fed to animals. I think these are particularly, because they're transposable elements. This is an area that my lab was very active in, that make them extremely pliable genetically.
Thank you for your question, for your presentation. We know that plants have a very low efficient rate of transforming...
Take it a little farther away.
Okay. We know that plants have a very low efficient rate in transforming solar energy into chemical energy. With the advance of technology, we expect plants to get more efficient with time, but nature has its own limits, and I wanted to know the role you think synthetic photosynthesis and synthetic meat production will play in the food chain.
People are trying to reproduce photosynthesis without wasting all that energy on making things grow. Will that succeed? I would make a guess that what you'll see is an increase in the efficiency of photosynthesis. You're seeing papers being published already on that. I think that'll happen before people reproduce the whole process in a simplified form. But one of the things that I think that it's worth throwing, and I would like to have thrown it into the section on transforming technologically, is something that at first sight seems kind of revolting, but that's meat that is grown in vitro. So tissue cultured meat, making it palatable is what people are doing now, and decreasing the price gives us a lot of breathing room in those planetary limits. And the reason is this. It takes about 2,000 liters of water to grow a kilogram of grain. If you want a kilogram of beef, it takes about 20,000 liters of water. And then you can look at it from a grain perspective. If you eat the grain, you eat the kilogram of grain. But if you feed it to cattle, you have to feed it 10 kilograms of grain. That's the feed conversion ratio. It may be 8. I've seen everything from 7 to 10 kilograms of grain per kilogram of meat. And of course, think about the land that it takes to raise the grain to feed to animals. So the good news is that people are becoming aware that eating a lot of beef is not good for them in terms of health. And so what you're seeing is, at least in some countries, a shift in diet to more fish and more chicken, mostly. So I think that's where some of the savings will come from. And another area, which I didn't have time to touch on, but which is extremely important, is food waste. So a lot of waste, a third to a half of food that is produced is thrown away or doesn't make it to market. Obviously, in less developed countries, the problems are more roads and the cold chain and so forth. In developed countries are very wasteful. And again, I think the good news is that you see more food banks, you see much more effort to utilize fruits and vegetables that are not perfect in some countries. Some countries are much more particular about how the fruits and vegetables look and throw away an awful lot. But reducing waste gets us at least a quarter of the way to being able to maintain our current food supply. You stayed a long time, and I appreciate that. Thank you very much. Oh, one more question.
Sorry, one more. Thank you so much for the nice presentation and for delivering some more optimistic messages than I'm familiar with. I'm not a plant biologist or have any experience with agriculture, so apologies if my question is a bit misjudged. I do remember reading in the past about one of the biggest threats to current food security as well as meeting the future demand is phosphorus from phosphate rock in being a finite source. And I seem to remember the problem being threefold in terms of one, demand exceeds supply, two, it's mismanaged, and three, there is no mechanism for monitoring availability of phosphorus. And I just wondered if maybe you had any thoughts or insights on that topic.
That's an area where a lot of improvement can be made in uptake, utilization. One particular area of genetic modification of pigs, for example, is for them to use the phosphorus and to break down the phosphorus more effectively. Yeah, we are reaching the limits of availability, not just of phosphate, but of nitrate. So potassium limitations may also be looming. But I think those are all solvable problems. I think one of the major issues is to make fertilization a whole lot more efficient. Much of the fertilizers that we apply to the land now is not used by the plant. Plants will take it up to a certain point, which is about 50% of what you supply them, even when you supply it in excess. So increasing uptake, improving delivery systems, all of that is in the realm of technology. So today, with herbicide-tolerant crops, we have tractors that go right over the stubble of the field, inject seeds with a shot of fertilizer, and that'll just improve. That just keeps improving every year. So I think cutting down fertilizer pollution is just enormously important.
Questions?
I think that was it.
I have
Again.
one. Not a comment, just a little one. In
Yeah,
fact,
everybody has to wait.
Oh, it's okay. No, it's just a comment. I think you used the word that is very important, that is belief. And the other one, change the diet. I think a harsh question that we live in society, in the cities, is how can we make people change their beliefs and change their diets? Because part of the solution would be that people look at their food differently. And how can we do that?
I don't think we can force people to change their diets or their beliefs. The question in my mind is, what does it take to persuade somebody? You're seeing that shift already. Unfortunately, it's mostly amongst the most educated people who are cutting down on beef consumption and increasing fruits and vegetables, because that's what the health community and the nutrition community is telling us is better for us. The belief question is the big pickle. So once people have the kind of beliefs that you saw up there, oh, it's bad for you. I know it's bad. I don't know what it is, but it's bad for you. That's a really tough one, and that's an area where I'm actually doing some research. We know that building trust allows people in a one-to-one interaction to build enough trust so that their minds are willing to process information that clashes with their belief system. We don't know how to do that on a very large scale. If we look at the medical community, people over the 20th century, we wiped out smallpox. We think it's a public health marvel today. But basically, people were rounded up, sometimes quarantined, forced to be inoculated. So those are government by force programs. And sometimes it really was by force. Same with polio. I don't know who could do that for plants. In agriculture today, we scientists have a much less memorable message than folks like Greenpeace and the organic food industry. They're telling you it's better for you, or that these things are bad, and anything that has a little fear around it is extremely difficult to dislodge, because that's the way we evolved. We evolved to run from things that are scary. Unfortunately, I wish I knew how to change that, but I don't. We're doing research on it. Our hypothesis is that if we connect, so very often, we heard this yesterday at the Scientific American meeting, people say, well, it's those big biotech companies, or they say it's not natural, or it's not safe. And when you dig a little bit, what's the beef with a big biotech company? It's that's about fairness. People think that's not fair, that people are making money off of seeds. So fairness is very deeply embedded in our evolutionary history. Our closest primate relatives have a sense of what's fair and what's not fair. They get mad at their handlers if they think the monkey in the next cage is getting more than they're getting. So those are kind of what we call our moral foundations. Respect for authority, religion, fairness, obviously healthfulness and safety. We don't want to eat things that will make us sick. So our question is, if we connect with those moral foundations, will we be more successful in getting people to stop and consider that there are there's a body of evidence that disagrees with their belief. And the answer may be yes, and it may be no. So that's what we're trying to do. Thank you for your time and attention.